So I'm Bram of Chia Network. So we're making a new cryptocurrency that has a new consensus algorithm that uses VDFs, and it works. Um, so what we're doing is Chia is based off of proof of space. Uh, Proof of space it does not use VDFs itself. I'm getting there. So the reason for using space instead of proofs of work is excess storage capacity is already widely distributed, and you could potentially tap into this resource that's much less wasteful than proofs of work and is much more widely distributed and not so centralized, which is the whole point of cryptocurrencies, is to not be centralized. So being able to do proof of space is very appealing. We actually have pretty good space algorithms, which we came up with, that are quite practical and are extremely low latency. So, improvement over the pebbling-based ones, which have malleability and practicality problems. So, if you have proofs of space, let's just assume we have proof of space working. There's some pretty big problems with proofs of space generally, centered around, well, you made it not cost anything to do your mining. That's an actual feature. The problem is when you have that feature, it enables attacks. So there's two kind of broad categories of attacks here. One of them is someone can remine since Genesis. Someone has some amount of storage capacity that's a small fraction of all the capacity today, but the capacity of the system has been going up exponentially over time. And if you take their current capacity times the amount of time that has happened historically, they will be able to make a chain that's heavier than the legitimate chain. And so we don't want that kind of attack. We don't want any checkpointing here at all to happen in the system. And second of all, there's grinding attacks. Someone can just try out zillions of different versions of the history and pick out the one that works out best for them, and now we're kind of back to doing proof of work again. Bitcoin doesn't have grinding attacks because grinding is just what you do. It's just decided in all its wonderful, horrible glory to be the honest behavior. So now we get to VDFs. You actually can fix this using VDFs. This is the Chia Green paper. It goes into great technical depth about this. But the basic idea is you combine proofs of space and time, which is the more poetic term we're using for VDFs here. And it's sort of analogous to work equals force times distance. So there's a work difficulty parameter like there is in Bitcoin that has normal work difficulty resets like Bitcoin does. This is all Nakamoto consensus. And the rule is that for each block, there's going to be a proof of space, and it's going to be finalized with a proof of time. And the number of iterations that the proof of time has to run for is going to be inversely proportional to the quality of the proof of space. And that fixes our problems. In terms of the VDFs that we're using class groups, and we are rotating the discriminant every single block. Just every block, hash the last block to generate a new discriminant for a new class group and run a VDF based off of that. The generator that we're using is we're specifically making it so that the discriminants are 7 mod 8, and in the class group setting A to 2, B to 1. This always makes a normalized element of the group and is perfectly useful as a generator. It's kind of funny because nobody ever complains about everyone just using 2 as your generator in like RSA-based time lock puzzles. And there's no reason to think that's good or bad or anything. Everyone just uses it, so this is kind of analogous to that. We're using a discriminant size of 1024 bits, which when this thing is going to die after 5 minutes or so, going down exponentially, is a pretty big security parameter to have there because it's rotating every single time. We have now done 2 VDF implementation competitions and handed out over $200,000 in prize money. So at least in terms of software-based implementations, we've at least furthered the state of the art of doing those for class groups, and we are planning on doing hardware stuff in the future when we have money for it. The proofs of time that we're using, because there's a separate proof of time output and the proof for it. It's kind of this funny thing that we have all these different techniques that actually make different types of proofs on the same underlying output. this really kind of separates into two different things. When the thing first finishes, you want super low latency. You want to immediately have a proof available to you at no extra latency from when the underlying calculation was finished. And then later on, you want something that's very compact and cheap to verify for the historical blockchain, but someone can calculate that slowly and inefficiently later because you got all the time in the world. If it takes like a day or so, who cares? It's going to be nice and compact in the historical blockchain. So what we're using, well, what we're going to be using. At this exact moment, our testnet is using n equals 3 Weslowski for everything. What we're switching to is making it so that it supports up to n equals 64 Weslowski. And the format actually lets you just use arbitrary numbers of iterations as your checkpoints there, which gives you huge amounts of flexibility in how you actually go about your proof system. And that does make it completely practical to make reasonably small proofs that are available just immediately. Later on, this gets replaced and gossiped around one Weslowski proof of the whole thing, which is as compact as you can get. The thing that's actually kind of annoying there is it's spending most of the time in verification in hashing to a prime, specifically in failing primality tests as it's hashing to a prime, because these are pretty big and most of the things fail. Because of that, it might be tempting in the future to put in a new and better proof of the output of the proof of time based on, I don't know, darks in a Jacobian group or something. Might want to give that a few more hours before switching to it. We currently have a running testnet. This is actually up and running. You can go to chia.net, download this stuff, run it yourself. Don't have transactions on our testnet yet. It's in alpha. It's going to be in beta very soon. It's gotten almost 1 trillion iterations of VDFs in it. It's actually working. As of sometime in the last few days, some entity out there in the universe started running a Time Lord that's faster than ours. We don't know how or why or what have you, but it's producing correct outputs, so it's doing something. We are going to have hard forks before mainnet launch, which is going to happen around the end of this year. In particular, going to do some tweaking of the VDF algorithm, not really any fundamental changes, mostly just cleaning up like how the hash to prime works and stuff like that in it. And that's it.
Any questions? All right.
So our thing runs at about 150 iterations per second, and someone has something running at about 190 iterations per second, or 190,000 iterations per second.
All right, thank you.